Okay, so thanks for inviting me. Again, so this is a joint work with Leonard Shield, yes, who at the time of writing the paper was still a bachelor student, yeah. So props, yeah, to him. And yeah, so I will start, yes, with introducing the very concept of fully homomorphic encryption. Yeah, so I guess, yeah, that many of you don't do really research, yeah, in FHE. So we'll start from the very basics, and we'll start with classic encryption. Yes, so let's say that we have a laptop and we want to communicate with our bank, yeah, and send some transactions, some data, yeah, about some transaction. And the obvious problem is, yeah, that some eavesdropper can eavesdrop on the communication and see our transaction data. So to solve this, we use encryption, and with a secret key on the right side and another secret key on the left side, the bank can decrypt our ciphertext. And then the eavesdropper, without this very special secret key, cannot make any sense, yeah, of the communication. Yeah, so this is still primary school. But this very simple idea really is what allowed us, yeah, to build the entire internet, yeah, as we know it today. Yeah, so all e-commerce applications, cloud computing, etc. Yeah, so all of this, yeah, is possible, yeah, thanks to this idea plus Diffie-Hellman key exchange, yeah, and signatures and so on. Yeah, so but the ideas, yeah, like from the 70s. Yeah. Now, with fully homomorphic encryption, we hope to put things one step forward. And this kind of encryption scheme, yes, is a very special type of encryption scheme where we can encrypt our, for example, medical records, yeah, or it can be like any data, with our secret key, send it to the cloud, and now the cloud, without any special secret keys, yes, can do computation on this data. Eventually, the cloud can send the outcome of this computation back to us, yeah, and we, having the secret key, are able, yeah, to decrypt the outcome of the computation, yeah, so the function on our message. Okay, and this, yeah, alone, yeah, has already like multiple applications, yeah. So for example, in privacy preserving malware detection, analytics on genomic or medical data, in financial systems, and finally in cryptography itself, yeah, and unlocks many really advanced use cases, yeah. So like MPC, let's say, or even obfuscation of a cryptographic obfuscation, yes, of code. All right, so how to build encryption like this? So we'll start, yeah, with a very simple system, a very simple linear system. And let's say that our secret key is going to be a vector of integers, S. And then to encrypt a message, which is also an integer, we will compute our inner product, yeah, between the secret key and some random values, yeah, and eventually we get a ciphertext C that is also a vector of integers. And now let's say that to decrypt, yes, we compute the inner product of the secret key S and the ciphertext C, and we get the message. Okay, and now let's have a look, yeah, at some computation that we can do on this sort of ciphertext. So from the linearity property of the inner product, yeah, of vectors, yes, we have, yeah, that we can already compute linear functions on this kind of ciphertexts, yes. So we can multiply it, yeah, or we can add two ciphertexts together, and when we decrypt this, we get the outcome of the computation. To do multiplication, it is also possible. Now, multiplication is a little bit more involved. Yeah, it requires to compute the Kronecker product, yeah, and so on. Yeah, but it is possible. Yeah, so for this presentation, it is actually not that important. Yeah, how to do multiplication. But for now, what is even more important is that this crypto system is completely insecure. Yeah. So if you notice, if we get, for example, n different ciphertexts, yes, then we can build a system of linear equations, yes, and simply solve this system for the secret key S, yeah, and we have a total break. So how can we patch this sort of system? Now, the idea is, yes, that we are going to add a random value to each ciphertext, yeah. So now, if you look at this linear system, the linear system will always be will always have more variables than you will have equations, yes, and we cannot solve such systems. The problem is, however, that now we cannot decode the message anymore, yes, because the message will be masked by this uniform, for example, uniformly random value E. So yeah, so for now, what we have is that either the system is completely insecure, or it is perfectly secure but useless because we cannot even do simple decryption. So the solution, to this pickle is to find a compromise, and what we'll do is we'll indeed add a new random variable, but we'll assume we'll only add random variables that are small, yes. So let's say that they occupy the first a few least significant bits, yes, of the entire message space, and then we assume that the message is encoded in the most significant bits of the message space. And now we can still do computation on this, yes, but you can notice that so when we compute, then we also compute on the error, and the error is gonna get bigger and bigger. But now this very simple patch, it turns out that even quantum computers cannot handle this, and solve such systems of linear equations, and in fact, so if you are familiar with the learning with errors problem, so this is more or less the learning with errors problem, Okay, and now again, so we compute on the ciphertext, yes, and unfortunately, computation will increase our noise. So in all really systems, fully homomorphic encryption systems, that we have today, where we can do addition and multiplication, the problem is, that we have to deal with noise, yes. So we have a ciphertext, we do computation, the noise gets bigger. We do more computation, the noise gets so big that it's eventually going to destroy our message, yes, and we won't be able to decode. Now, the idea to handle this, was introduced by Gentry, in 2009, and among others, so he got the Gödel Prize, for this very idea. And now, okay, so we do some computation, for example, addition or multiplication, which is relatively fast, really. So it takes 8 microseconds, it's like below a second, but it increases our noise, Now, to decrease the noise, we'll build a very special circuit, and publish a very special ciphertext that encrypts the secret key itself. And now with this special ciphertext, we compute homomorphically, or like on the encrypted data, the decryption circuit. And the decryption circuit, it gets rid of the noise, it rounds out the noise and so on, So eventually we'll get a ciphertext of our function, but with smaller noise, and we can still keep computing, on this on the resulting circuit. If the noise gets too big again, then we bootstrap again, and so on and so forth. So it seems that all problems are solved, so we can compute relatively fast, if the noise is too big, we simply compute the decryption circuit homomorphically, and the noise is small again, and we keep computing, the problem is, that this bootstrapping is relatively slow and so on, So for example, if you have a fully homomorphic encryption scheme, that computes arithmetic circuits, to bootstrap something like this, it takes around like 3 minutes. Yeah. And for Boolean, it is a little bit better, so 0.2 seconds. Yeah, so it seems that it's that this is going to be practical. But yes, so if you want to compute some even very simple functions like a 32-bit multiplier with a Boolean certificate, so we just designed the certificate. Yeah, and you can calculate. Yeah, so one bootstrapping per gate, yeah, and the certificate, yeah, and you end up, yeah, with 6 minutes, yeah, for a elementary operation. So that's a problem. So how to address this problem? Yeah, and the idea is so okay. Well, the biggest problem is that really the efficiency of the bootstrapping. Yeah, so that's the problem, yeah, that we want to address. And the idea is that all right. So since we have to bootstrap anyways, so what if we could design a very special bootstrap that does some useful computations along the way? Yeah, so we get rid of the error, but alongside getting rid of the error, yeah, we'll compute a useful function. Yeah, and it turns out that it is possible. Yeah, so we call this functional bootstrapping. So in this paper, we show a special case, yeah, of functional bootstrapping, and yeah, and we designed this as follows. Yeah, so at the core of the so the very idea of the blind of the bootstrapping is as follows. Yeah, so remind that yeah, the decryption, yes, of a ciphertext is a almost linear function. Yeah, almost, yes, because it is linear. Yeah, but we have this this error e here and so on. Yeah, that's why it's like almost. And okay, so we'll define a procedure that is called blind rotation. And in this blind rotation, yes, so we'll have a vector of, again, integers. We'll take as input the ciphertext C. And now we are going to homomorphically rotate this vector, yeah? And this rotation, so it is according, yes, to the linear decryption of the ciphertext C with respect to the secret key S and so on. Yeah, and now, yeah, you will see that the first or like the last value in this vector, yes, is going to point at the decryption of the ciphertext. Yes, so it is going to be indexed by the scaled message, yes, and the error. And eventually the trick is, yes, that we are going to set this vector. So we're going to set this ace in such a way that the last value will point at some function m and so on. Yeah, and this is already without the error. Okay, and remind you that all of this will happen on encrypted data and so on. Yeah, so the whole rotation circuit and so on, we compute this homomorphically without really knowing, yeah, the secret key. And now, so how to handle the error? Yeah, and to handle the error, yeah, the trick is that we will encode the f from m, yeah, so the function on some messages in intervals and so on. Yes, so if the error is let's say 0, 1, 2, 3, 4, yes, but it's bounded and so on, yes, then even if we add a little bit of error and or subtract a little bit of error from m, then we still end up within an interval, yes, and we will extract, yeah, still f from m. Yes, so this is how we do this rounding step. All right. Okay, so how to now implement this rotation in practice? Yeah, so this is now a little bit more involved. So first, yeah, let's denote, yeah, this the decryption or this linear function here as r. And now, so remind you that we had this vector and we want to rotate it. Yeah. And now in practical schemes, yeah, we operate really on ring LWE, and we will represent this vector as a polynomial in this very specific ring. Okay, So you don't need to really know why this ring and so on, yes, but yeah. So what is important is that in this ring, if we multiply such a polynomial by x to the r, what we get, yes, is negacyclic rotations, yes. So if r is smaller than n, so n is the degree of this polynomial, then then we rotate the coefficients, yes, but the least significant coefficients and so on, yes, you'll see that they change the sign, yes. So now earlier we had like plus a n minus r, etc. Yeah, so now we have minus, yeah. If r is equal n, then we rotate, yeah, the entire polynomial, yes. So we flip it, yes, and all the coefficients change their signs, yeah. And then, yes, if r is between n and 2n, yes, then yeah, then we rotate again, yes. The least significant coefficients are positive, yes, and the most significant coefficients are negative, yeah. So if you want to encode now this functions, yeah, on this vector, yeah, the problem is that we don't really know where we are, yes. Is our r going to be smaller than n, equal n, yeah, or is it going to be bigger than n, yes. And because of that, yes, the only functions, yeah, that we really can realize are negacyclic functions. And this means, yeah, that so a negacyclic function, yeah, so it means that yeah, if we have a message x modulo p, yeah, and we shift this message, there's a typo, should be small x, yeah. If we shift this message x by p over 2, yes, then we get minus f from 1, yes. So these are very specific functions that we can compute, and this is really a problem, yeah, that prevents us, yeah, from computing many functions that are interesting, yeah. So to solve this problem, we came up with the following scheme, and yeah, so we get as input the ciphertext, which is our encoding, LWE encoding of the message M. Then we do a first blind rotation with a polynomial that is going to compute the bit, yeah. So this bit b, yeah, this is going to indicate, yes, whether the message encoded, yes, will be bigger than yeah, bigger than p over 2 or smaller than p over 2. And now if we have this bit, yeah, then it's very simple. So we implement our choice circuit, yeah, but it is like a choice circuit that has a additional key switching scheme integrated, and eventually we get a ring LWE of our poly b, and this poly b, so these are now polynomials that are going to define our function f that we want to compute while bootstrapping, yeah. And eventually we run the final bootstrapping step, yes, and the final blind rotation step, yes, and eventually we get the LWE from f from m. So this is the very high level overview of the algorithm. Yeah, the specification of the algorithm itself, yes, is, I think it takes like 3 pages, yes, or more in A4, and the secure, so the correctness proofs, yeah, are even bigger, yeah. So that's why the paper got so long. But okay, so we implemented the scheme. So in the paper itself, there are in total 7 different parameter sets. Yeah. So if you are like interested, yeah, in the very details, yes, then you can look at the paper. But these different parameter sets, they target different security levels and different correctness levels. Yeah. So one a pair of parameter sets, yeah, targets. I think a 7-bit plaintext space, yes, and another one targets an 8-bit plaintext space. So the implementation that we did, yeah, was at the time done on top of Palisade. And so it is today it is already a little bit dated, yeah, because so Palisade is no longer supported. but yeah, so to follow up work, yeah, we come in a second. So here I'll give you a very rough comparison, yes, to a naive Boolean circuit implemented in TF-HE. Yes, so let's say that we want to compute a lookup table, which is like a 7 to 7-bit F, yeah. And now if we implement this lookup table as a Boolean circuit, yes, and then for every gate we run a Boolean bootstrapping. So even if the Boolean bootstrapping is faster than ours, yes, so in total, this sort of computation will take 0.2 of an hour, yes. Whereas for us, yes, so it's just one bootstrapping. We compute the entire function in 13 seconds. Similar with multiplication, yes. So if you need to compute a Boolean circuit, yeah, that does multiplication of a 7 and 7-bit number, of two 7-bit numbers, then with a Boolean circuit, it will take us 43 seconds, yeah, whereas with FDFB it takes 26. And then where FDFB like really shines, yeah, is that if you want to compute a linear or an affine function, yes, and then a lookup table, yes. So for FDFB, we can handle affine functions in a native LWE. Yes, so this is only addition of two vectors. Yes, and then bootstrapping will still work correctly. And this is where we get the speed up. Yeah, so you can see that computing this entire function, yes, is as fast as this. Yes, and that's because computing this addition here, yes, so this linear function here, it's basically for free. Yes, it takes like nanoseconds. If you want to compute all of this, yes, represent this as a Boolean circuit, yes, and compute bootstrap for every gate, yeah, then it's gonna take almost half an hour. If now this linear function is bigger, yes, so it's of size like 800, yes, then for Boolean it's going to take almost 12 hours, whereas for us, yes, it's still 13 seconds, yeah. Now, so this is just a comparison, yeah, for the sake of the presentation, yeah. So in the paper we have more examples and applications, yeah, where this FDFB really works well, yes. And one is that we can handle bigger integers, yes, using the Chinese reminder theorem, yeah. So the idea is that instead of computing modulo 2.7, yes, we can compute modulo a prime number, of course, yes. And then from the Chinese reminder theorem, yeah, we can build bigger numbers, yes, modulo a composite, yeah, and do the computation in parallel. We can compute multivariate polynomials, yes, and finally we have some example applications, yeah, for neural networks, yes. So you can see, for example, this function, this is already a neuron, yeah, let's say, yeah. So if f is a ReLU, yes, or function, yes, then yeah, then you already have a neuron, yes, and then you build your entire circuits, yeah, out of or your neural network out of these atomic functions, yes. Now finally, what is worth to mention is that okay, so this timings, yeah, so the like this comparison is that for arithmetic modulo a power of 2. So this means, yeah, that for the Boolean circuit one, yeah, we don't have to implement modulus reduction, yes. If this would be a prime number or something like this, then here you would have to add the time, yeah, to compute modulus reduction. Yes, and good luck. I never saw something like this implemented in practice and so on. Yes, so whereas for us, we just natively handle this, yeah, already in the plaintext space. Yes, so the timing doesn't change. Yes, so it can be a prime, it can be whatever number and so on. Yeah. Okay, so this is it, yes, when it comes to techniques. Yeah, now the paper really appeared on ePrint, I don't remember really, yeah, I think 2001, yeah, something like that. But very soon after, yeah, so there were some follow-up works, yes, and notably by Liu, Michanchu, and Polyakov, yes, so they improved, yeah, and the Tota paper. Yeah, so they improved quite significantly the general idea. And what they need, yes, only like 2 blind rotations. So in our paper, we actually need a little bit more blind rotations than 2. But yeah, so eventually there was also my paper on the CCS, yeah, which basically took, yeah, this 2 ideas, yeah, but implemented this, yeah, using the N2 assumption instead of the ring LWE assumption. And the timings nowadays, yes, are around 0.3 seconds instead of 13 seconds. Yes, so we had like over the last 1-2 years quite an improvement. Now there was also a concurrent work, yes, by our team from Ciliotti, Linger, Orfia, and TAP. Yeah, so this was published on AsiaCrypt 221. However, until this day, I'm not aware of any implementation of this system and so on. Yes, so any implementation or suggestion on parameters. So I didn't see them. Maybe they exist. Yeah, who knows? But as for future work, yes, so as you can see, so like if you want to do full domain functional bootstrapping, the cost for a single bootstrap, yes, is still a little bit higher than for a bootstrap, yeah, that doesn't do, or for a bootstrap, yeah, that is negacyclic, yeah. So so now at best, yeah, we need 2 blind rotations, yes, and we would like to do this, yeah, with just 1 blind rotation and so on, yes. So that's still an open problem. Yes, I hope, yeah, that is gonna be solved, yes, in the very soon, yeah. But yeah, so stay tuned. Yeah, there are still some ideas, yeah, to improve the method in general. And okay, yeah, so that's it, yeah, for now. I think I'm in time. And if you have any questions, yeah, then yeah, feel free.
Thank you for your talk. Maybe we have the time for a very quick question, but we are a bit late on schedule, so otherwise can be taken offline. Okay, so we are a bit late. So thank you a lot.
So thanks for the presentation. Congratulations.
I will have one.
Sorry.
I'm here. Sorry. So it's an amazing work. I was wondering whether the construction that you propose is compatible with bootstrapping, because it's a part that is critical in the efficiency of arithmetic homomorphic encryption. And to me, it seemed like you were getting rid of packing in order to do the rotations on the values.
So again, whether it is compatible with approximate arithmetic circuits and so on. Yes, FHG. Aha, or this. No, so at least not immediately and so on. Yes, so we targeted circuits, yeah, that are like overwhelmingly correct and so on. Yes, so there are no approximations. Now, so I saw some papers, yes, that tried to apply to, yeah, this idea, yeah, to Bootstrap, yeah, CKKS, ciphertext, and so on, yes, but yeah, so okay, in short, you can do this and so on, yeah, so it is possible. Whether it is actually practical and so on, yes, hard to say. Yes, so here, as you see, we were able, yeah, to like handle plain text space of like max 8 bits. Yes, and this is already with pretty large ring dimensions and so on. Yeah, so in CKKS, yeah, I guess, yeah, that people want to target plain text spaces that are more accurate than just 7 or 8 bits. So I don't know. So it depends maybe on your application, yes, and then it may make sense and so on. Yeah, but if you want to bootstrap something, yeah, that okay, you need 30 bits of precisions, yes, then our method won't work well for you and so on. Yeah, for arithmetic circuits, yeah, again, you can realize large integers, yeah, using CRT, but this doesn't tolerate any errors there. Yeah, so yeah.
Okay, thanks for the answer.
So let's thank the speaker again. The next talk is PASTA, a case for hybrid homomorphic encryption from Christoph Dobronik, Lorenzo Grassi, Lukas Elminger, Christian Reichberger, Markus Schaffnegger, and Roman Walch. And Roman will give the talk.
Thank you for the introduction. So let's wait for the slides. So yeah, welcome from my side as well. So this talk will be about a different aspect of homomorphic encryption, namely hybrid homomorphic encryption. So when we come back to the typical homomorphic encryption use case, we usually have a server-client architecture where the client has some data set and the server wants to compute a function on this data set. And to protect the privacy of the data set, usually the client first encrypts its data set with a homomorphic encryption scheme, sends it to the server. The server then can perform the function on the encrypted data set, produces an encrypted result, sends it back to the client, and the client who knows the decryption key can actually get the result in plain. So besides the huge performance overhead we get on the server side by employing homomorphic encryption, we also have a different problem with this example here. And this is called ciphertext expansion. And the problem here is that when we want to encrypt some data set with a homomorphic encryption scheme, then the resulting ciphertexts are usually significantly larger than the plain text. And this can significantly impact the performance of the whole use case chain, especially when we have a client, which is an embedded device, which has, for example, a very limited bandwidth connection. So to give you a feeling on how large this ciphertext expansion can become, so this highly depends on the homomorphic encryption parameters, but for some examples that we have in the benchmarks in our paper, the ciphertext expansion can increase the size of a 250 kilobyte data set to more than 7 megabytes. And this is already a factor of more of 30, and it can easily become larger with different homomorphic encryption parameters. Luckily, there exists a solution for this ciphertext expansion, and this is called hybrid homomorphic encryption. And the main idea is that we use symmetric encryption scheme in combination with homomorphic encryption schemes. And the way this works is the following. Now, in addition to having an homomorphic encryption key, in addition to having a homomorphic encryption key, the client now also has a key for a symmetric encryption scheme. And in the setup phase, the client first encrypts the symmetric key using the homomorphic encryption scheme and sends this ciphertext to the server. And now when the client actually wants to send some data sets for an actual use case, it now encrypts the data set using the symmetric encryption scheme, which does not have a ciphertext expansion. So here the upload has exactly the same size as we would have sent the plain text here. But unfortunately, since we now have a symmetric ciphertext on the server side, the server cannot really apply the use case anymore. So it first needs to transform the symmetric ciphertext into an homomorphic ciphertext. And it does this by evaluating the symmetric decryption circuit homomorphically using the encryption of the symmetric key here. So this step basically transforms the symmetric ciphertext into a homomorphic ciphertext. And the server then can proceed as before by evaluating the use case on the homomorphic ciphertext. So while this approach is very nice, so it completely gets rid of the ciphertext expansion, it of course has some disadvantages as well. So it is immediately clear that the workload on the server is significantly larger than for just evaluating the use case. So it has to evaluate the symmetric decryption circuit on using homomorphic encryption, which already adds some overhead. But we get more problems in homomorphic encryption schemes where we don't have an efficient bootstrapping procedure. Because in these schemes, the performance of the homomorphic use case usually scales with the multiplicative depth of the circuit we want to evaluate. And of course, also this symmetric decryption circuit adds to the multiplicative depth. So the performance gets even worse. And that is also the reason why we usually do not want to use traditional ciphers like AES for hybrid homomorphic encryption, because these ciphers were not really optimized for minimizing the multiplicative depth, and therefore the performance penalty would be too large on the server side. So to summarize hybrid homomorphic encryption, what we do here is basically trading off data transmission size with additional workload on the server side, and we do not want to use ciphers with a large multiplicative depth here. But luckily, the academic research has been very busy with coming up with new ciphers. And I want to give you a little bit of an overview of the state of the art in this field. So here on the slides, I've depicted a timeline here from the left to the right and some different homomorphic encryption schemes. So the main focus of this talk will be about PGV and BFV, which basically allow you to encrypt larger prime field elements up to about 60 bits. Then they're also backing friendly, more on that later. Then there is the CHES schemes, which works internally very similar to these schemes, but they allow for real numbers as plain text. And we have a different branch here as well with DFG, which initially was optimized for fast bootstrapping on binary values, and then got optimized for fast bootstrapping for larger integers now up to 8 bits. And the bootstrapping procedure we heard from the previous talks, they basically apply here. But unfortunately for these libraries here, we don't really have an efficient bootstrapping procedure yet. And when we now bring some ciphers into the game, so into the picture, we see that there have been a lot of different symmetric ciphers proposed in the last, I would say, 7 years. And most notably, we have, for example, OMC, Raster, and also Philip here on the slides. But so far, all the ciphers that I have shown you before, these ciphers are basically binary ciphers. So they allow to encrypt bits as plain text, and the circuit is also built using AND gates and XOR gates. But this also has a disadvantage when we have some use cases, for example, in CHES or BFV and BGV over larger integers, because to be able to homomorphically evaluate the decryption circuit, we must instantiate the homomorphic encryption scheme to work over bits, such that we can actually evaluate the AND and XOR gates. But however, when we don't have an efficient bootstrapping procedure, we cannot really transform a ciphertext that encrypts bits to a ciphertext that encrypts larger prime field elements. That also means that when we want to use these binary ciphers in hybrid homomorphic encryption, we also must translate the use case afterwards into binary circuits, leading to additional slowdown of the whole use case chain. And that disadvantage was realized by many different research groups. So the focus shifted on designing ciphers which actually operate over the native field for the different homomorphic encryption schemes. And our approach is a cipher called Buster. So when we bring these new ciphers into our picture here, we will see that there are basically 2 ciphers optimized for BGV and BFV. That is our approach Buster, which we will talk later in this talk. And there is a competitor roughly came out at the same time, which is called Master. We also have 2 ciphers which come in addition with a framework that allows hybrid homomorphic encryption for CHES. And there is also a cipher called Elizabeth, which is optimized for the updated requirements in the advanced DFG library. All right, so in this talk, we are mainly focusing about this branch here and our cipher Buster. So let's talk about our cipher itself. So what are the design goals that we had in mind when designing Buster? So as I said before, it's we want to be working on the native field of the HE schemes that we target. It's mainly BGV and BFV. So the cipher should also naturally operate over larger prime fields. And since we don't really have an efficient bootstrapping procedure in the schemes for larger prime fields, we also want to minimize the multiplicative depth of our cipher. That means the cipher must be built from a low number of rounds, and each round must be evaluatable with a very small multiplicative depth. So while this is very good for performance, this is actually very bad for the security of the cipher itself. And so we will have to trade this off with operating over a larger internal state of the cipher, which is required, as I said, for security against especially algebraic attacks on the cipher. And therefore, we will also optimize our cipher to be as backing friendly as possible. So more on that, as I said later, such that it can be efficiently evaluated in BGV and BFV, even though we have a very large state size in here. And before I talk actually about Buster, I want to first introduce Raster, which is one of these binary ciphers also introduced for hybrid homomorphic encryption. And it is depicted here on the slides. And it works basically as a stream cipher where we apply a cryptographic permutation on the key to produce the key stream here. And what is so special about Raster is that it's, as you can see here, these affine layers, which basically are matrix vector multiplication followed by a round constant addition. And in these affine layers, the matrices and round constants are pseudo-randomly generated from a nonce and a block counter. So basically, whenever we want to create a new keystream block here on the output of the cipher, we basically have created it with a randomized version of the cipher. And this is very crucial in already preventing a large class on attacks on a symmetric cipher, namely attacks which require more than one plaintext ciphertext pair to work. And this is basically the main ingredient which allows us to build a cipher that is secure with a very small number of rounds. And the competitor that we mentioned before, this master cipher, is basically a translation of raster to the FP setting. Now let's talk about our design, the Buster design strategy. On the first hand, it looks quite similar to raster, and that is because we are also using the same design strategy in pseudo-randomly generating the affine layers from a nonce and a block counter to, again, prevent all attacks which require more than one plaintext ciphertext pair. And but other than that, the design actually has some major difference to raster. And the most obvious one here is as well, you can see we basically split the design in two different branches and apply two independent permutations on these two branches, followed with a mixing step after each affine layer. And the reason for that is, again, backing friendliness. And for that, I now want to introduce how backing actually works in BGV and BFV. So as some of you may already know, in BGV and BFV, we can not only just encrypt one field element into a homomorphic ciphertext, but we can actually encrypt a whole vector of field elements into one ciphertext. And whenever we want to apply homomorphic addition or homomorphic multiplication on this ciphertext now, these get applied as homomorphic element-wise vector additions and element-wise vector multiplications on the underlying plaintext. So this backing basically allows us to parallelize a lot of operations on our plaintext. And in addition to these element-wise vector operations, we can also perform vector rotations on these encrypted plaintext, and we can do this by employing Galois automorphisms. And there have been many different algorithms proposed in the literature which are optimized for this backing structure for BGV and BFV. For example, in matrix vector multiplications, which we also require for our Buster cipher, there exists an algorithm called baby step giant step optimized diagonal method. And this basically just uses vector additions, element-wise vector multiplication and rotations, and this is super efficient for matrix vector multiplications. But in this BGV and BFV, actually the Galois automorphisms do not really result in a rotation of the whole vector, in a linear rotation of the whole vector. And in fact, the rotation structure actually depends on the homomorphic parameters. And you may have come along the ring LW parameters of homomorphic encryption, which are reduced modulo x to the power of n+1. It's a very common and very efficient parameter set of homomorphic encryption. And in this parameter set, the rotation structure actually is also very nice. And you can think about it as when we encode a vector into a plaintext or ciphertext in the schemes, we can actually think about it encoding two independent vectors. And when we apply Galois automorphisms, we can either rotate both of these vectors at once or just swap them with, So this is the structure in these special rings of the LW schemes. And we actually, when we want to evaluate Buster homomorphically, we make use of this special rotation structure in these rings. And namely, we have these two branches of our cipher. And when we encode the first branch into this first vector and the second branch into the second vector, then both branches actually get evaluated completely in parallel. And this reduces the homomorphic runtime of evaluating Buster basically by half. And also this mixing step, which we have after each affine layer, this can also be implemented very easily using this Galois structure. Namely, this is equivalent to just adding this, the vectors to itself and adding a swapped version of the vector itself. It's also an operation that we can perform by Galois automorphisms. So as I said, by applying this backing structure, the runtime gets basically reduced in half. So the rest of the design, we basically just have to cover the S boxes here anymore. And as I said in the beginning, we want to focus on low-degree S-boxes, and so we are mainly using this Feistel S-box here, which basically we square element and add it to the next one. It's basically the simplest quadratic S-box, which is invertible, which we came up with. And in the last round, we employ a different S-box to boost the degree of the cipher to get better resistance against algebraic attacks. And here we use the well-known Kubing S-box here. Then as a result, we can actually get, based on our security analysis, secure designs with as low as 3 and 4 rounds. And for these 3-round designs, one branch needs to consist of at least 128 field elements to be secure against algebraic attacks. When we compare this to master, they need 4 rounds to basically produce the same low number of keystream elements. And when we increase the round by 1, you can see that the minimum state size in one branch gets reduced to 32. So this, so you can also trade off the size of the cipher with the number of rounds here. So that was basically everything about Buster. Let's have a look at some benchmarks that we made in the paper. So the paper is accompanied by a very huge benchmarking framework where we implement most of the ciphers we have seen on the previous slide in several different HE libraries. So for BFV and BGV, we are using SEAL and HElib, and we also have some benchmarks in the original C++ DFHE library. So not the one that is currently pushed by Sama, but the original one, which basically just has this binary interface for encryption. And this framework, everybody can use it. It is publicly available on GitHub, and it is also part of the CHES artifact evaluation progress. So regarding benchmarks in the paper, so we not only evaluated the runtime of homomorphically decrypting asymmetric ciphertext, but we also combined it with some DOI use cases to get more meaningful benchmarks here. And the first use case I want to talk about is a very small use case. So it's on purpose very small. So it's just a 5x5 vector matrix vector multiplication on 16-bit integers. And this use case is here to show you that binary ciphers are actually very, very inefficient in hybrid homomorphic encryption. And here are some benchmarks results. So on the y-axis, we have the runtime in seconds for both first the homomorphic decryption of the symmetric ciphertext and the actual use case. And this is a logarithmic scale here. And on the x-axis, we have the noise that is introduced into the ciphertext during this evaluation. And here we have depicted a lot of different binary ciphertext, and you can see the fastest one, which is ArcRaster here, already requires several hundred seconds to evaluate the whole use case here. So you can see these even though the use case is very, very small, the runtime is super high already. So that the picture changes a bit when we introduce some finite field ciphers. So here on the rectangles, we have Buster, the 3-round version, and the 4-round version. Here, these two are the master design, and here we have Hera, which is another finite field cipher. And you can see here the runtime is significantly faster compared to the binary ciphers, and also our cipher Buster produces the lowest runtime and also the least noise introduced into the ciphertext. So this was for just for reference, what would happen if you use AES? So this would be on top here somewhere up there. So it would be very inefficient and introduce a lot of noise in here as well. So this was a very, very small use case to basically highlight the need for finite field ciphers in the first place. In the paper, we also benchmark some different use cases. So we go into different prime fields from 17 to 60-bit. We have a larger depth use case, and we also increase the width of the matrices to make the use case itself even slower, to get a better feeling on how hybrid homomorphic encryption basically affects the use case in general. So for the results on these benchmarks, I want to refer to the paper. Talk is quite long already, but long story short, Buster also outperforms its competitors in these use cases as well. So to conclude my talk, in our paper, we focus a lot on hybrid homomorphic encryption, which is basically a trade-off between client data upload size and server runtime. And we have seen that we require in cipher which is of very low multiplicative depth. Otherwise, the use case would be very inefficient. And in our paper, we are the first to basically investigate the trade-offs also on the client side, not only on the server side. We have some extensive benchmarks in several different libraries with use cases, and we came up with our own symmetric cipher, which is optimized for hybrid homomorphic encryption in BGP and BFV. So the paper is available on ePrint, of course, and our benchmarking framework is on GitHub and also in the de facto evaluation of CHES. So that basically concludes my talk. Thank you for your attention, and if you have any questions, please don't hesitate to ask.
Thank you, Roman. Are there some questions? Yeah, Ingrid.
Slide 7. On slide 7, you also have a Brown algorithm.
Yeah.
Rubato. And
yes,
it's not in your code. It's not green, it's not orange.
So the
so I mean, not binary, not prime.
The thing is, Hera is actually a cipher over FP. So it's basically similar to Basta and Master, and that's why we also included in our benchmark. Rubato can be seen as a more general version of Hera with an additional twist. So it also introduces Gaussian noise into the symmetric encryption. And this makes it kind of incompatible with what we do in BGP and BFV. But since in CHES they also introduce noise into the ciphertext, Rubato can be perfectly usable in these schemes as well. So it's basically Hera with a smaller number of rounds plus addition of Gaussian noise.
Okay, thank you for the extra information.
Thank you.
Yeah.
Okay, I want to ask, how about other machine learning methods using hybrid homomorphic encryption? The performance, is it impractical or not? Because here you only give the result on the small integer regression.
Yeah. So basically the main problem we still have with these libraries here is that when we don't have an efficient bootstrapping, then we also cannot really evaluate larger neural networks. So that's the main issue we have here. So we are limited with these libraries for when we want to do machine learning with smaller networks. When you have to go, when you want to evaluate a machine learning model with a very large depth, you're kind of forced to use these libraries here because they have a more efficient bootstrapping procedure. But they come with other disadvantages. So we heard this in the talk before. So most natively, they work over just 8 bits. So they need to have some tricks with CRD encoding to get larger precision. And they also don't have backing as in these schemes here. So the performance might be worse for smaller depth neural networks, but larger networks, you need to use these libraries, but their performance will get very slow.
Okay, thank you.
Yeah. That's basically the main issue we have in homomorphic encryption, that even though there's a lot of progress being made, still the results tend to be kind of slow.
Is there a last question physically? No. Okay. There is one question online. I will read it to you. Why did
there's
we...
also one here. So
I don't know for another question.
Which one first?
Yeah, so physical.
Well, first of all, thank you very much for a nice talk. I am not very familiar with all these ciphers, but you mentioned at some point that one of the trade-offs that you had to make in this family of ciphers is to reduce the number of rounds and increase the size of the state in order to counter, as a countermeasure against algebraic attacks. Do you have any idea on how, for a given security level, these sort of ciphers compare to, let's say, ciphers with larger rounds and smaller states when it comes to algebraic attacks, whether these are maybe a bit more vulnerable to algebraic attacks, or are they similar in terms of security?
So in general, the methods how we analyze this are the same as for AES. But we have different trade-offs here, because when we go to larger prime fields, usually algebraic attacks become more important than statistical attacks. You can see this also in ciphers for MPC and zero knowledge. So in this special setting where we have these randomized affine layers, we kind of have protection against statistical attacks already in there. And also against attacks like higher order differential attacks and so on. So the main attacks we are focusing on here with these ciphers are just columnar basis, linearization, and similar. So this setting allows us to throw away a lot of attacks already in the design phase, and so the security analysis is basically simpler, so to speak. But the drawback is, of course, that these designs, they are very useful for slow settings like homomorphic encryption. But when we would compare the plain performance to something like AES, so encryption outside of homomorphic encryption, you will see that they are significantly slower. So that's the reason why we only see this design strategy in combination with slow primitives as homomorphic encryption.
Thank you very much.
And very quickly to finish, the question online is, why do you use random matrix in the diffusion and not MDS matrices?
Yes, so the same answer here. So we want to have these random matrices to randomize the whole cipher. And this prevents a lot of attacks. So when we would have fixed MDS matrices, so this would be better. So if we would have fixed MDS matrices, then we would have to deal with all these attacks which require more than one plaintext ciphertext pair, and especially higher order differential attacks do not work well together with low depth ciphers. So we kind of need to randomize them to get this low depth. And there are techniques to get randomized MDS matrices as well, but they are slower and plain to generate, and we did not see a huge advantage there. So that's why we didn't do that.
Okay, thank you. So let's thank the speaker and the speaker of the session.